This is a joint work with my colleagues in Stony Brook, Sebastian Raymond Johnson, Zhuang Shen, and my advisor, Long Lu. So first of all, what are the execution units that we are mentioning, that we are talking about here, and why do we need a more fine-grained one? So there are two execution units exist in the current OSs. So namely the processes and threads. And the distinction between them is that processes have separate address spaces, while threads, they don't. They share one if they belong to the same thread group. And this model has been used for decades. It runs very well, but it doesn't match with the modern app development paradigm, where multiple components from different parties get put together into one single application. And this model cannot defend against a class of attacks that we try to address in our work. So this attack is termed by us in-process memory abuses. Here's the definition. Basically, if there are malicious or compromised components, they try to steal data or execute code of other components running in the same process, then we call it in-process memory abuses. Let me give you two examples. The first one is about stealing secret data. Remember the Hubley bug from 2 years ago. If the attacker can exploit the vulnerable OpenSSL library, then he is able to steal the sensitive data from the web server process, such as private keys or login passwords. And the second example about executing private code. So in iOS applications, there are those private APIs gets loaded into the user address space of the applications, and this opens up a window for the attackers to find out those APIs and then invoke them during runtime to do harm to the system. And certainly, the threat of in-process abuse has been there since the day one of this model of virtual memory. So there are certain techniques out there that could be the potential mitigations of this problem, but they are only doing it either partially or paying too much prices. So the first line of work belongs to the process level isolation. So basically you put different components into different address spaces and then use different processes to run them. You can find this approach being adopted to OpenSSH and Chrome. But the problem with it is that IPC is very expensive, but this approach heavily relies on IPC to do data exchange or synchronizations, etc. Also, the adoption efforts is relatively high because you're basically splitting monotonic applications into multiple components. Let alone if you can do this or not, even assume that you can do it, it's still kind of difficult because you now have to deal with those concurrency issues, which is very error-prone. And the second line of work belongs to the software fault isolation. One example is Google's native clients. So note that because of the threat model of native clients, it can only address a subset of in-process abuse problems because it requires to instrument the untrusted code, which means that it's ineffective on the dynamically generated or the external code. And the last line of the techniques belongs to the hardware-assisted techniques, such as Intel's SGX or ARM's trust zone. In terms of security, these techniques are doing well, but in terms of usability, for example, in Intel's SGX, it's being overly restrictive. For example, when the code running inside the secure environments of the SGX, the code cannot even make system calls. Also, in ARM's trust zone, you bring up this semantic gap that you need to fill up with. So it's kind of difficult sometimes to use them. With all that being said, we want to propose threads. You can view threads as arbitrary scope segments of the thread executions. On the left-hand side, on this figure, those are red lines scoped by the dashed rectangles. Those are the threads. And what's special about a thread is that each one of them gets to have a private memory pool allocated from the same virtual address space. And this private memory pool can only be accessed by the corresponding thread. And we term them out as pool. Also, we have a set of thread APIs, and that's backed by our OS level support and for the developers to use our thread system, which I will show you in the later slides. So because we need to operate at OS level, we assume a trusted OS, but there are untrusted components in the victim process, which means that other components in that process subjected to the attacks of these untrusted components. So now allow me use a high-level example to better illustrate the idea of threat. Using the case of doing password authentication on web server. So the scenario is that the client will send the password to the web server, and the web server will compute the hash of this password and do the authentication, etc. And this is the virtual address space of the web server process. So you can see the yellow bars are where the plaintext password located in. So in case of an in-process memory abuse attacks, there is a malicious component. In this case, it's a malicious library, and if it wants to steal the sensitive data located in these two user address in these two areas, then it's very difficult to defend against that. But with threat, what we can do is we can put those sensitive data inside the S pool, and only the corresponding authentication threat will be able to access them. So in case of malicious components, again, this attempt to steal the secret data will be blocked by us. So now I want to show you two sets of threat APIs. The first set is called threat creation APIs, namely threat enter and exit. So the idea is that whatever code running in between the invocations of these two API are called running inside thread. And as you can see, threat enter takes one argument called put descriptor to indicate which S-pool this thread is bounded to. And we have a second set of APIs called S-pool allocation APIs. They function similarly to the glibc, malloc, and free. So the idea is that you call them inside a thread to allocate or free memory inside the S-pool. Now allow me to show you the code example, like how to use those thread APIs. Again, using the same cases of doing password authentication on web server. This is the code listing from Lighted, which is lightweight web server. So basically, when the web server sees there is a coming authentication request, it will just call thread enter to make this password pool available. And then you can call SDS init, which is the wrapper of the S-pool allocation APIs, which I will show you in the next slides. And then you can allocate the memory inside S-pool. Then the web server can store the sensitive data inside the S-pool, then call thread exits to lock this S-pool down so that no one else can access it later. And on the left-hand side are the S-pool allocation wrappers. And on the right-hand side, which is the code for the authentication thread. So very intuitive. You just call thread enter again to make this S-pool available. Then you can do the computation to access this memory, just like they are the normal memory. And then after you're done, you call SDS free you can free this chunk of memory for later use by other components. And then you call thread exit to finish this thread execution. Okay, so now let me show you the overview of our thread system. Basically, we have two major components, S-driver and S-compiler. So S-driver is the OS module that will deal with those runtime events such as thread entry, exits, or S-pool allocation, deallocation, etc. And on the right-hand side, the runtime view of our thread system. So what's not mentioning here is that we actually allow multiple threads to share the same S-pool, because imagine a scenario that there is a encryption and decryption threads. They might want to share the same set of crypto keys. And we also have a way to prevent the attacker from abusing this feature, which I will show you in the later slides. So now let's dive into the S-driver. I want to show you how we build the concept of S-pool. Basically, we utilize the ARM memory domain mechanism as our building block. But before I move on, I also want to remind you that Intel has a very similar mechanism called memory protection keys in the upcoming CPUs. So the design that I talk about here can be very straightforwardly applied to the Intel as well. But for the sake of this talk, let's just focus on ARM. So on the right-hand side are the page tables structure of ARM architecture. And as you can see in the first layer page table, you can basically tag them with different domains. In this case, we have domain 1 and domain 14. And also in the system, there are those domain access control registers. So they function just like their names. By assigning value into them, you can basically control the accessibility of different domains on the corresponding core. Those registers are banked, just for your information. And in this case, we have domain 14 is accessible and domain 1 is not. So based on our memory domain, it's very intuitive to build the concept of S-pool, but still we have several challenges to deal with. The first one is that the granularity of the assessing subject can only be checked at the CPU level or at the corresponding core, but we want something more fine-grained. So we create a notion of thread so that the assessing subject can be recognized at the thread level, and then we can use S-driver to manage them. And the second limitation is that there are only existing domains available in the systems, so we cannot naively allocate a new domain whenever a new S-pool gets allocated, because it does not scale. So the solution to that is that we statically bind an accessible domain to each CPU, and then we reuse that domain for multiple S-pools if they are accessed from the same CPU but not at the same time. Let me use a high-level example to show you how this works. This Q face represents a dual-core system, and the two eyebrows represent the two domain access control registers. As you can see in the entries of them, if it's gray means on the corresponding core, this domain is not accessible, but if it's colorful, it means the other way. So the two eyes represent the two cores, and the mouth represents the virtual address space of a process that is using our thread system, and the two teeth represent the two S pools that belongs to two different threads. So if there's a thread number 1 running on the yellow core, now it wants to access its S pool number 1, what we do is we assign the domain of this S pool to the yellow domain so that this thread can access its S pool, but no one else can. And if at the same time another thread running on core number 2 wants to access its S pool number 2, we do the same thing, except that we change the domain of that S pool to the orange domain. So the result is that both of them can access their own S pools, but not each other's, because this is prevented by the domain access control registers set up there, as you can see. And when they're down, they call thread exits. So we assign the domain of their S pools back to the gray domain again. So to sum up, S-driver will lock the S pool when thread exits, or when its context switch out while the code running inside a thread, or during some asynchronous events such as signal handling, etc. And you will unlock the S pool for those opposite events. So we want to optimize our system by moving the domain adjustment of the critical path a little bit, because adjusting the domain is relatively cumbersome, because you A, need to do page table working, and then B, you have to invalidate the corresponding TLB entries to make this change take effect. So how we do that is that, remember there are two knobs that could control the accessibility of S pools. The first one is the domain of the page table entry. Yeah, the second one is the value of those register entries. So we use the second way to move the domain adjustment of our critical paths, because changing the register value is much, much faster. It only takes one instruction as highlighted there, and it takes effect almost instantly. The only problem is that now even the legitimate domain access could trigger the domain faults. So we developed the domain faults handler to lazily handle the domain faults that triggered by different events, such as if it was an attack, then we will abort the program, or if it's a legitimate domain access, then we will help the program recover from that domain fault. So other than those things, S-driver will also provide certain runtime events. The first one is the secure stacks. So the idea is that each thread has a secure stack allocated from its own S pool, and we switch the stack during the thread enter and other events, because we don't want the sensitive data or computed by a thread to be accessed by other components in the process. And also, there are certain system interfaces that S-driver needs to take care of, such as if the attacker wants to purchase the code running inside thread, or try to directly read a sensitive value from the physical memory or from the I/O channels. S-driver will block those accordingly. And here's another component in our system, S-compiler. S-compiler will do the following things, such as A, verify the correct thread API usage, and B, remember this share S pool feature that I mentioned previously. So how S-compiler do this is that by associating each thread with its S pools at the compile time, and then it store that information in the generated binary so that this information can be registered to the S-driver during the load time of the program. And also, S-driver will do certain flow analysis and instrumentation to, for example, hardening the control flow of the in-thread code, or do some data flow checking to prevent the in-thread code from accidentally propagates the sensitive data from the S pool area to the unprotected memory. For more information, please refer to our paper. For the reason of time, I need to jump to the evaluation. So we prototype our system on top of Raspberry Pi 2 monobit with the Cortex A7 processor, which has only 1 GB memory. And we adopt right into these 5 open source softwares. We choose them because intuitively, each one of them has some sensitive data to protect, for example, like the login password or the OpenSSL, the private keys. And for the record, in our evaluation, we only protect one kind of sensitive data for each one of the softwares. Because we're not the developers of them, it's kind of difficult, if not impossible, for us to identify all the possible sensitive data that they have. And regarding the adoption efforts, on average, we only introduced 21 lines of code changing into them, and it only took us 32 minutes to adopt right into them. Because the adoption process is very straightforward. Once you know what data or code you want to protect, you just find the code that access them and wrap them with the corresponding Shred APIs, so minimum code change. And regarding the performance, we observed less than 5% slowdown. Some of them because of the system call, some of them because the instrumentation code added by the S compiler. And on average, we saw less than 8% memory overhead. And here's another evaluation result. We want to compare the Shred APIs with the corresponding system costs. So our ground truth is this get PID, which is one of the lightest sys costs in Linux. And we compare Shred creation APIs with clone. Here, clone is the one that creates a thread. So Shred enter and Shred exit, as you can see, Shred creation APIs run slightly faster than clone and almost twice the time of get PID. And also we compare the S-pool allocation APIs with mmap. Here, S-pool allocation runs slightly slower, but this is actually expected because they are the wrappers of mmap. So to conclude, our goal is to help developers to protect their sensitive code or data from in-process abuse. And to achieve that goal, we propose shreds with private memory. Shreds are fine-grained. You can view them as flexibly scoped segments of thread executions. And shreds are efficient and compatible because we're based on MNU domain check. And we don't introduce multiple page tables. We don't have nested pagings, no heavy instrumentations. And lastly, no hardware modifications. So you can just grab our driver and buy an ARM machine and use our system. And also, the last but not least, shreds are robust because we not just prevent the attacker from attacking Shred from the code outside, even if the attacker manages to find vulnerability for code in Shred, we also make sure that the chances the attacker pull this attack off will be negligible. So that concludes my talk. I'm happy to take questions.
Thanks.
Hi, thanks a lot. So this may be in the part where you said, I don't have time to talk about this, so read the paper. But how do you keep the evil library from just calling shred enter with some other S-pool and reading the data off of that directly?
Yes, thank you for the question. So this is actually this feature called S-pool sharing. And I also mentioned in the talk that how the S compiler prevent this attack from happening is that at a compile time, S compiler will try to associate each Shred enter call site with the S-pool descriptor and store that information at the generated binary additional ELF section. And this information will be registered to the S driver at the program load time. So if there's a malicious library, try to call Shred enter with other Shred's S-pool descriptor, it will be rejected by the S driver. So,
okay, thank you.
Brian Ford, EPFL. Nice work. I especially like the attention to the kind of API simplicity and stuff. I am a little concerned you didn't describe the threat model very too much. I'm concerned that, if the attack code can kind of live anywhere and do a lot of other things in the library. Why wouldn't the attack code just try to say cause your replace the shred-based password hash checking code with its own version that doesn't use shreds, by fiddling with a function pointer or some DLL DLL loading state or something to just kind of redirect the whole password checking module to something that the malicious library controls.
So yes, this attack is actually valid, and in our current implementation, we requires the source codes of the libraries or those things, and during our compile time, we will do the program analysis for all the modules together, and I'm not sure if I understand the question.
We can discuss the details offline. It's just
sorry.
kind of unclear what the separation between the trusted part of the code and untrusted is. I'd like to, but yeah, we can take that offline.
Thank you.
No, good stuff.
I can fix that. So what you need to do is you need to associate what code is with a shred so that you can't control flow inject out of a shred to the library. Alternatively, just use Intel SGX and encrypt your code and your data. If you can stand the overheads, it'll give you the same ability today.
Yeah, SGX is very secure in that sense, but the problem is that, so in the enclave, the secure environment in SGX, the code cannot make system calls. So it's kind of, for some cases, that it's kind of difficult to use them. For example, there are some papers before that have to throw in the whole OS in the enclave to make the applications work. So in that kind of scenario, if you are willing to sustain the security guarantee that we provide, then I think our solution is actually easier to use. So
in either case, though, you've got to draw lines around stuff. You're just doing thread calls. SGX has got to do more like the Chrome style sandboxing. But thank you. Very interesting.
Okay, thanks.
Go ahead.
Hi, Paul Mikowski from NARF Industries. Thanks for the talk. So my question is regarding memory protection keys. So you talked a lot about ARM protection domains, and that would require kernel involvement to change the protection domains. But for the memory protection keys, my understanding is you can just issue new instructions in user space that would write to those keys that would hold whether or not you can read or write to different domains. So I guess my question is, does your compiler instrumentation ban instructions? Would you have to do something like NACL where you have a verification pass to make sure you don't have off-cut instructions that represent those instructions?
Okay, so yeah, what you said is valid, and I think you also kind of answered the questions that you raised. So yes, in the memory protection keys, the user level code can change the value of their registers. But what we can do is that, fundamentally, the designs will still be mostly the same, except that we could use compiler techniques to sanitize the code to make sure that there's no gadgets to change there.
Have a verification pass as well then? Is that correct?
Yes.
Okay.